We're very pleased to help us wrap up this theme to introduce Professor Matthew Barth. He's a Yeager Families Professor at the College of Engineering at UC Riverside, where he's a professor in electrical and computer engineering and also director of the Center for Environmental Research and Technology at that same institution. He graduated from the University of Colorado and then received his master's and PhD at UC Santa Barbara, and he's been at UC Riverside since 1991, a good long time. We had a talk on autonomous cars 2 or 3 years ago by someone from Berkeley who told us that it's going to be decades, if not longer, until we really see these come into play. So it'll be interesting to see what Professor Barth's opinion is on that. So it's a great pleasure to welcome you, and look forward to your talk.
Thank you. All right, well, thank you for that introduction. So we've been doing different work in this sort of connected and automated vehicle arena some time, and mainly looking at impact analysis. And we'll go through some of the different projects we've been working on and talk about various aspects of that. So very quick outline. I'm going to talk just very briefly about our research center down at UC Riverside, and then talk about our larger National Center for Sustainable Transportation, which funded a lot of this work. And then very quick introduction about connected and automated vehicles. I think a lot of people in the audience know quite a bit about automation and the vehicles themselves. And then really get into the more in depth about the impact analysis. And we'll talk about things like safety, mobility, environmental factors, and things like that. And then just sort of summarize one of our more recent papers of what we did and kind of comparing, what are the trade-offs and what are the benefits between safety, mobility, and the environment. All right, so very quickly on our research center. And so again, I'm from the University of California, Riverside. It's one of our more younger campuses. Our College of Engineering got started roughly about 26, 27 years ago. And then one of the key parts of the college was starting up this new environmental research center. And this kind of highlights the different parts of where we do research. Obviously, a lot of it's focused on air quality, looking at different types of vehicles, measuring those vehicles, seeing how we can improve, reduce the amount of criteria pollutants. We're also looking at greenhouse gases and those type of emissions as well. We got into sustainable transportation because of those direct linkages between transportation and air quality. And so a lot of it was assessing what is the impact of all these vehicles on the roadway, what is the impact of congestion. And then we started thinking about solutions and really what are the solutions to solving the air quality problem. And along the way, we want to reduce congestion along the way and then keep things safe. So that's really what we do within the Sustainable Transportation Group. We look at secondary air quality issues, how other type of air pollutants are formed. That's part of what we do. And then tie it in with energy. So energy is a big thing, too, in terms of the types of fuels we use and then the growing trend to go more and more electric, right, the electrification of vehicles and things like that. So it's a pretty unique research center of different disciplines, different engineering disciplines that have gotten together. We're doing more and more with policy and also with our School of Medicine. So that's what we do at our research center. I mentioned a lot of this research so far has been sponsored by our National Center for Sustainable Transportation. This is a research center that's national. It involves 3 universities within California. It's headquartered out at UC Davis, and then we're partners at Riverside. USC down in Southern California is also part of it, Georgia Tech, Vermont, and we, of course, look at these sustainable transportation issues. This has been in existence now for 3 going on 4 years, and it just got funded to go for an additional 5 years. So this has been a very active research group between different campuses. Okay, so let's start with connected vehicles, right? So for years and years and years, we've built our cars, and over time, we've introduced more sensors on those vehicles, more intelligence on the vehicles in terms of interpreting, what's going on with the vehicle. We've done better in terms of actuation. We've increased safety with airbags and traction control and all these different things. But we haven't done too much with cars actually talking to cars and cars actually talking to the infrastructure. And just as you can imagine with cell phones and all the connectivity that we have today, why not take advantage of that, and why not use that to benefit traffic in some way? And so that's what a connected vehicle is all about. And this sort of leads into more about the automation piece as well. But this is something that, we knew it was going to come, and really the major research here was, what are the protocols for having vehicles talk to each other, vehicles talk to the infrastructure, but maybe more importantly is what kind of benefits can you get out of doing that, right? So can you do things such as improve safety, and can you get better traffic flow, and can you reduce emissions and other negative environmental effects? And so there's been different deployments. I think if you go all the way back to 1997, there was a famous demonstration that happened down in San Diego about how do we create these automated connected vehicles, how do we get them so they're talking to each other, they can form these platoons to increase the traffic flow, do things safely, and then there's going to be environmental benefits from that too. So things have really advanced. Again, communication technology's come a long ways, and now we're at the point where we have that connectivity that we can use. So the U.S. Government has seen this coming, and they've developed a number of different programs. And then a lot of what I'm going to be talking about today are back to the three key cornerstones, right? We're going to talk about safety issues, mobility issues, and when we talk about mobility, it's things like travel time and how efficiently you can get from one point to the next point. And then our forte at our research center has always been the environmental piece, looking at the air quality, looking at the pollutant emissions as well as the greenhouse gases. But more recently, I would say our graduate students and others are now starting to branch out and look at, how does safety interact with the mobility parameters and the environmental parameters. And really that's the result of our latest paper. Safety, of course, is probably the number one thing we think of when we think of why are we doing this connectivity and why are we doing this automation. We want to make things safe. If you look at the number of deaths on our roadways in the U.S. on an annual basis, it's still around 35,000 people die every year. And the whole idea is, can we employ this connectivity, the automation, and hopefully drive that down to zero. But at the same time, we want to reduce traffic congestion. We want to be able to have reliable trips where we can go from one point to the other point and knowing how long it'll take to get to that destination. And then, there's several things that are working in favor of the environment. We're getting cleaner cars. We're doing things such as we're smoothing traffic flows. And so all these things are adding up so that our air quality is improving in terms of the transportation component. So the U.S. Department of Transportation did some pilot programs over the last 5 years or so. The major one was a safety pilot that took place in Ann Arbor, Michigan, that instrumented several thousand vehicles and basically showed how safety can quantitatively improve if you have this communication between vehicles. And a lot of that's going on to potentially become rulemaking, where our vehicles after maybe 2019, 2020 will be required, just like we're required now to have airbags, will be required to have radios in our car that have this communication capability so that cars can talk to each other and avoid crashes. And so that's really the driving force of why we are doing more and more in connected vehicles. But there's also many mobility advantages here, right? So you can implement specific applications that smooth traffic flow, get better dynamics within the traffic. It's essentially getting rid of the stop-and-go effect. And you can do that by improving the communication and the reaction rate between vehicles. A lot of our stop-and-go effects are due to human delays. Just a second or two in terms of how we react to brake lights and things like that start that stop-and-go pattern. And if you have this communications that talk within milliseconds, then you kind of get rid of those delays and this sort of slinky effect that causes a lot of the congestion we see today. And then, a lot of studies that show that, if you are doing the smoothing, if you're getting rid of these unnecessary accelerations and decelerations, that, of course, is going to be less energy that's needed to move our vehicles down the road, and it's going to be less emissions. And it's a pretty nonlinear effect. The accelerations are much, much more highly polluting than what you would see just from a mild one or a steady state cruise. So that's the type of work that we've looked at our research center, is trying to quantify what are the impacts of these different activities that vehicles do on emissions. There's a couple pilots going on right now. One's focused on safety with trucks. Another one's looking at deployment in New York City, so more of an urban type of set of applications. And then yet another one in Tampa, Florida. So there's kind of been an explosion of different activities. Certainly the U.S. Department of Transportation sponsored pilots, but also cities are saying, hey, we want to get on board sooner than later. We're going to require radios in vehicles. Why don't we start working and putting in the appropriate infrastructure to instrument our traffic lights, so the traffic lights are able to talk to the vehicles. So many cities around the country are starting to do that in anticipation that they're going to take advantage of these different connected vehicle applications. And then I think a lot of people have heard of smart cities, right? So this is a component of smart cities. We want to do things smarter in terms of energy use, in terms of transportation, and all the other aspects of what would make up a smart city. I know you can't read this in the back, but it really just displays, there's well over 100 what we call applications, right? So if you break it down to what are the safety applications, what are the environmental applications, what are the mobility applications, a lot of people have been thinking about, what can we actually implement if we had this communication capability. So things like curve overspeed warning, things like emergency electronic brake lights. That's where the car knows that the brake light comes on very quickly instead of seeing it from a human driver. A lot of things in the environmental side. We're going to talk more about this eco approach and departure. That's where traffic lights are talking to the cars and telling, this is my signal and phase information, and it allows the vehicle to kind of adjust towards that traffic light. But like I said, there's a whole list of this. If you go to this CMRIA database, it's online, it explains this and talks about the protocols and things like that. So there's a lot of creative applications that will have pretty significant benefits in these three areas of safety, mobility, and the environment. And it's not just the U.S., right? So there's a lot of worldwide applications going on. We talked about the different deployments in the U.S., but there's probably equal amount of effort going on in Europe and in Asia too. Okay, so then let's talk about the automation piece. So maybe one of the first things I want to talk about is differentiating between what is an automated vehicle and what's an autonomous vehicle. So you might have heard this where, when we think of autonomous, we think of a vehicle that has its own sensor set, its own sensors that has the ability to see other cars and interact with other cars and the infrastructure. But it's pretty much self-contained, right? It's based on the vehicle itself having that capability and being able to do some degree of automation just solely based on those sensors. And then when we talk about automated, it might include that same level of capability, but also including the communication piece, right? So the main reason I want to differentiate there is that I think we're going to see a lot more upside on a full automation that incorporates both the sensing, the onboard intelligence, as well as the communication. And I'll show some examples of that. A lot of sensing technologies come up to really make a lot of this possible. Radar systems, LiDAR system, laser ranging, and that goes on. Computer vision is a big part. And it's been in many papers and articles talking about the different levels of automation, right? So the Society of Automotive Engineers and our National Highway Traffic Safety Administration have come up with different levels where you look at level 0, which is no automation, that's humans driving around, with different incremental improvements and increases in automation to where you get to level 4 and level 5, which are full automation. And that's often what we hear about in the papers about when are the cars going to be fully automated, when they're going to be able to drive completely by themselves without any kind of human interaction. So one of the first questions you might ask is, well, what's automated vehicles going to do to traffic, right? Is it going to improve it? What's going to happen with safety and all these other factors? So back to the differentiation between autonomous and automated, it's been shown, both in simulation and some real-world experiments, that if you have just pure autonomous, where you're doing it purely by sensing, we're probably not going to see a lot of big improvements in terms of mobility and environmental impacts. Again, you're not really, you still have to sense vehicles, and there's still that little bit of time lag that causes those same problems we have now with humans. But again, if you replace that with communications, you cut that reaction rate way, way down to where you can get better traffic flow at higher speeds and smoother traffic flow that has that positive environmental benefit. And so, we already have some technology on board now, right? So these adaptive cruise controls, this is where you set not only your speed of what you want to go at, but how far do you want to follow the vehicle in front. So the adaptive cruise controls now still have to use radar to sense the vehicle in front, and they slow down and they speed up, but there's still a time lag, and again, it's been shown where that's not a huge improvement in terms of improving the flow rate on the roadways. But if you now look at what's called cooperative adaptive cruise control, include that communication piece, that's something where it's very clear that you can get much better flow rates out of that type of situation. So I think the key lesson is, when we talk about all this automation, we're going to call it connected and automated vehicles, because you really need both of those components to make this work. And really, that's kind of what this diagram is showing, is where the autonomy comes together with the connectivity, creating the connected and automated vehicle. Okay, we're going to talk a lot about these three cornerstones I already mentioned: safety, mobility, and the environment. So we have to have measures of effectiveness, right? We have to have some way of measuring the performance of these things. And a lot of this is measuring these things in the real world as well as in our simulation, right? We have to do a lot of simulation, mainly because we have to anticipate all these weird scenarios that, that need to be tested when you introduce a new algorithm or a new application for these vehicles. So these are pretty obvious, right? Number of collisions, the spacing between vehicles, all these different safety factors. Mobility has a lot. The typical one we think is what's our travel time for getting from one point to another, delays in the system, level of service, all these things. And then the environmental parameters, of course, are how much energy do we need to do our trip, and then what are the pollutant emissions and what are the greenhouse gas emissions. So we typically, when we evaluate an application, would be to sit there and come up, and if you're doing it in simulation, is to have different kind of modules that estimate those values, and then we can quantitatively compare, how much safety did we improve. So we usually run a baseline that says, here's a situation without any automation. We measure these parameters, and then we introduce the automation, do it in simulation, do it in a pilot, measure the same thing, and we usually say, hey, this application just improved the environmental parameters by 15, 20%. And safety went up by a certain amount. So that's really how we want to do this type of quantification. And so to date, a lot of what we've done in terms of this application development, it's usually for a specific reason, right? So we do things such as emergency brake light warning for safety purposes, right? We don't want to collide with the vehicle in front. And so, that's a definite safety application. And then we might do something like speed harmonization on the roadway to improve mobility. And we might do this eco approach and departure at traffic lights for environmental reasons. And so these applications, just as that list showed, is they're usually categorized in one thing. But the whole idea of the recent research project is to look for these synergies and potentially trade-offs, too, between the three different areas. And so we kind of created this Venn diagram that shows, obviously we want to be in this center part here where whatever we do, it has improvements in safety, mobility, and environment. But there are already cases that are shown, if you improve safety here, maybe it's at the disbenefit for mobility, and vice versa. If you improve mobility, maybe it's doing it slightly less safe than what we were doing before. So that's the whole point of our research project, is to try to analyze which applications are going to do well under different situations and try to understand a little bit better. And a slide a little bit later on is actually some tuning we can do. We can actually take some of the parameters of an application and tune it. So it might be somewhere over here, and we want to drive it more towards that centerpiece where we have benefits in all three parts. It's also important to point out what we consider as direct effects versus indirect effects. When we talked about direct effects, it's usually operational, right? So you get smoother traffic flow, or you have different reactions between vehicles. But an indirect effect might be something like induced demand, right? And so this comes up all the time with automated vehicles. If you had a lot of inexpensive automated vehicles that you can go out there and buy, it's pretty clear that the number of uses of those vehicles would increase pretty tremendously. So you have probably a large increase in the total vehicle miles traveled if everyone had automated vehicles and were making trips by doing that. And so that's an induced demand effect, and of course that has negative consequences in terms of mobility and energy in the environment too. So that's part of what needs to be studied, are those indirect effects. They might even be more important than the kind of incremental direct benefits that we get. So let's just take an example of platooning. So I'm sure everyone's heard of vehicle platooning. The whole idea is, can we get cars to travel in these strings much closer together? And it has all sorts of benefits, right? So one is, if you have vehicles moving at decent speeds kind of close together, that increases the flow, the vehicle flow down that roadway. And then if you do it with trucks, you get another benefit too of this drafting effect, right? If you get these two trucks close together, then there's an energy reduction here in terms of the load placed on them. There's actually a slight benefit for the leading truck as well. So that drafting effect has been shown both experimentally and in simulation that there is potentially a 15% fuel economy benefit by doing platooning. But then back to that trade-off issue, right? So as you get these trucks or cars closer and closer, the potential for something to go wrong where there's some kind of collision increases. So potentially safety might be a disbenefit as we increase the spacing between vehicles. So that's just to illustrate the type of analysis of what we're trying to do is, if we implement this as an application, what happens to those different factors of what we see there? And then, back to that tuning thing, it might be where we adjust the spacing so that we reach some peak in terms of safety while we're still getting some benefit in those other areas too. So that was just one example. This kind of highlights a little bit more about these indirect effects. This whole concept of explosion of various uses, right? So, if we had automated vehicles, we might do a lot more, right? We might not have to worry about, a long commute. We might put our time into something else where the automated vehicle is doing it. And then, things like young and disabled travel, all these things is just certainly going to drive up the VMT. And so the whole thing is, well, how do we deal with this behavioral effect where it's pretty clear that the number of uses is going to go up? And then back to the operational effects, that's where we can get that net decrease through the smoothing effects and things like this. This was a chart from a study that was done a couple of years back. And again, it's just looking at what are some of the different things we can do with automation. And everything on this side of the line is a benefit, and everything on the other side is a disbenefit. So platooning, again, if you look at the energy and emissions, we have a benefit simply because we have that drafting effect. But if you go down to things like the cost of travel and the ease of travel, that's going to cause that induced demand, and therefore that's going to be a net negative from an energy perspective. But this is the type of analysis of what we want to look at, and again, not just the operational side, but the behavioral side as well. Okay, then the other question is automation itself, and where do you apply that automation? And it's not something where you apply automation and all of a sudden that vehicle has complete capability to drive, right? So there's these incremental steps, and it happens at the powertrain. So there's different opportunities to do things such as energy management in your plug-in hybrid vehicle. Emission control systems are things you can control in some automated effects. Things like starting and stopping engines. Vehicle dynamics is one we typically think of. This is where we can follow a very prescribed speed trajectory, and the control system will be able to follow that a lot more precisely than a human driver. So a lot of automation happens at that vehicle dynamic level. And then you look at other things such as traffic flow, so you can start to now think about infrastructure automation, and that's improving flows along the roadway itself. And then eventually if we have automation, it may even reach into the infrastructure itself, where we change the size and the shapes of our roadway systems and the other parts of how we interact. So keep in mind, it's not just simply throwing automation at the vehicle in terms of vehicle dynamics. There's all sorts of things that are going on there at different levels. So just very quickly, I talked about it's important to analyze this in simulation. It's important to have these field studies that we can sort of see this. This is just to show you some of the tools, right? So there's some pretty sophisticated traffic simulation tools that can be coupled with emission models and other things that kind of give us an indication of safety and other factors as well. So it's really bundling up all these evaluation tools, putting them together, and doing the proper analysis. Again, I won't go into any detail too much on this, but it's really, you take a specific application, you put it into the simulation platform, and then the end result is you get these safety factors, the mobility factors, and the environmental factors. So let's just give some examples and some of the work that we've done in the recent times. So one is a program that happened out of the U.S. Department of Transportation called ARIS, and there was probably about 15 applications that were designed very specifically for improving, reducing emissions and reducing energy consumption. And so we'll go through some of those examples. And so here's the list of some of those things that came out of the ARIS program, and I highlighted, this is potentially a 10% savings in terms of energy, a 5%, 6%. So a lot of these things are somewhat independent, but you can add them up to get a larger total benefit if you implement things like eco approach and departure, traffic signal timing, signal priority, all these different systems that fit together. Okay, so this is one of the leading applications that has a pretty substantial effect on energy use and emissions. It's called Eco Approach and Departure, and it's simply taking advantage of communications between a traffic signal and a vehicle itself. And so the idea is the traffic signal, it knows what its signal phase and timing will be, and if it just simply broadcasts that out for vehicles to listen to it, a vehicle can use that and do things such as maybe speed up slightly to get through a green light, or slow down ahead of time so that it's not doing a hard braking event when it gets the signal. So this has been studied a lot, and there's a lot of work in the literature. Again, just showing different scenarios about a vehicle can speed up slightly, slow down slightly, but it's adjusting the speed of the vehicle to take advantage of getting through that traffic light. And in general, a vehicle by itself operating without any other vehicles around is typically a 15 to 20% improvement in the energy consumption if you do this. And this is easy to do, right? It's not hard to retrofit our traffic lights, and it's happening in various cities so that that information is being broadcast, the vehicles can listen, and then we can adjust to the speed. This is just a quick simulation example. It's running faster than real time, but what a typical set of vehicles coming into a traffic light might look like. And here you can see this eco approach and departure kind of smooths it out in terms of anticipating the light, speeding up, getting through, and then slowing down a lot earlier. But as I mentioned, this is a 13 to 15% difference in terms of how much energy you're consuming between those two different scenarios. This has been implemented in a couple pilots. One of them has been at the Turner Fairbanks Highway Research Center in McLean, Virginia, where this is studied pretty comprehensively and taken a vehicle, running it through the traffic light many, many times to prove that it is a 15 to 20% improvement. And it's ongoing, right? So now it's doing it with traffic to show what that benefit could be even in different traffic conditions. And then there's all sorts of variations. It depends on the signal timing. It depends on your algorithm, how much congestion you have, how much levels of automation. I should mention that in some of that testing at Turner Fairbanks was with automation on board, and the comparison between a human driver getting advice on how to speed up and slow down, that might be, as I mentioned, 10 to 15%. When you automate that, you get a lot better following of that trajectory. That pushes it up to around 20 to 25%. So getting, having the vehicle do that speed up, slow down automatically does give you that greater benefit. We also did tests on El Camino Real in Palo Alto. And if you're familiar with that, there's a number of traffic lights. They're about 100 meters apart, 200 meters apart, and fairly high levels of congestion. And it just goes to show that when we implemented this eco approach and departure, we didn't see a huge benefit. It was just in the 2 to 5% level, mainly because this doesn't work well when the things are already congested. There's not a lot of room for vehicles to speed up and slow down. So by implementing this when it's already congested, it doesn't really do very much for you. But again, that just gives you an indication of a real-world implementation. Other very quick examples. Speed harmonization. This is a mobility thing where you try to smooth traffic flow, get rid of those shock waves that occur on the roadways. If you analyze it under different penetration rates of the technology, different congestion levels, it's typically around a 5 to 10% energy benefit. If you, back to when I talked about adaptive cruise control, if you make it cooperative, you can get pretty significant energy benefits when you place vehicles in these loosely coupled platoons as they go down the road. So again, all these are results based on the traffic simulation models giving us those answers. Other things, not just designing trajectories, but how you travel through the roadways. So this is Southern California, right? And we've looked at a lot of truck patterns going from the ports down here in Port of Long Beach, Port of LA, and driving out to, say, warehouses in the east end of the Los Angeles basin. And there's a lot of choices for what route you want to take. And so truckers now typically choose the route that's going to be the least amount of time or the shortest distance. But part of what you can do is you can route trucks differently to minimize what their emissions would be, what their energy would be. And then you can even take into account things like disadvantaged communities where you want to route trucks away from those. And so a whole new slew of routing algorithms are coming out that are very valuable in terms of reducing the air quality impacts on the community and saving fuel for the vehicles themselves. One thing that we also do in addition to simulation, so we do these traffic simulations here, we're starting to now take output of these models and physically drive a dynamometer. So this is like a smog check where you put a vehicle on there, and so a vehicle traveling down the roadway here, you're turning the vehicle at that same speed, allows you to kind of get a better estimate or better measurement of what the actual energy and emissions would be of that particular vehicle. So if you had, for example, a futuristic vehicle that wasn't on the road, you could test it in this fashion and get a good idea of what the implications would be in the future. Other things, instrumenting vehicles, I mentioned that it's not just about trajectories, it can also be about the powertrain, about how to use your energy at different times. A classic example is your plug-in electric vehicle, perhaps a bus in this case, where you can use batteries in some cases and internal combustion engine in other cases, and you can intelligently choose, again, to minimize some kind of impact. Car manufacturers are starting to do this. They have their own applications, lane speed monitoring, different things like this. So again, these are things that we're helping the auto manufacturers develop with them. Real quickly, on the controls of intersections, right? So we have stop light or stop signs. We have stop lights there in the upper right. And then if every vehicle had the communication capability, you really don't need a traffic light. You can just talk to each other and get through that intersection. Pretty crazy. This is kind of like intersection in India or someplace like that. But we talked a little bit about this earlier, but all it takes is one or two of these non-automated vehicles to really mess it up. So this is kind of maybe not the right way to go. Instead, something like automating a roundabout makes more sense. Roundabouts are good because there's less potential areas of conflicts compared to an intersection here. And so if I was to redesign intersections with automation, this is probably a much smarter way to do it. We don't use roundabouts so much in the U.S. mainly because they break down pretty early in terms of traffic flow, mainly because humans don't merge very efficiently. But if you have automation, then you can get those efficient merges. And some students did some evaluation of that. So we'll speed up a little bit here. Okay, so back to these analysis. So we spent a lot of time going through the literature, reading the papers, pulling out these different parameters, and trying to find, what are the different things that are going on here. And it's in a recently published report as part of the National Center for Sustainable Transportation. I think that's going to be up. If it's not up already, it's up on the NCST website that outlines a lot of those different results. So again, it's this type of list. It's looking at vehicle applications, infrastructure applications, traveler applications, looking at all these different measures of effectiveness, and lots of literature. I know this is not easy to see, but it's really, it just shows you the number of papers that we're looking at in those different areas. What's the conclusion? The conclusion is almost all of the applications so far have really had a strong safety focus, right? Out of just the sampling, 25 there, 18 focused on mobility, and then, a decent amount that's focused on the environment. Not too many that have looked at things such as, hey, let's try to improve both of these or potentially both of these. We saw a few, but again, I think we're starting to see more and more where people are looking at that more holistic, all-encompassing, where we want to consider all three of those together. So again, read the report. It talks about the different types of applications, which ones are good in some senses, which ones are not as good. But one thing I mentioned a little bit already, one thing you can do with a lot of these different applications, if you're sort of in one area, you can start to change parameters to kind of drive it to where you get the maximal safety plus mobility plus the environmental benefit. And this is what's happening now when you're doing design such as the automated buses and different applications such as that. All right, I think because of time, we're going to go through this very quickly. Again, this is all in that particular report that talks about these different things and some examples, right, in terms of lane closures, cooperative adaptive cruise control, pre-collision systems, emergency electronic brake lights, all these different things that are highlighted in that particular report. One thing we dive more deeply into some applications. This one is a lane speed monitoring one. This was research that we're doing with Honda. And we look at different simulation scenarios of different penetration rates of the technology and how much it affects, again, the safety, mobility, and environmental aspects. This is a real-world implementation looking at the 210 in Los Angeles. And then we start to look at what we call radar plots, right? So looking at the safety issues, the mobility issues, and the environmental issues. And the blue triangle is the baseline, and then the red, of course, depicts, as we increase the penetration rate, how those factors change as you increase the number of vehicles that have that technology. So this is the type of analysis of what we're doing for that project. All right, so yeah, and this just summarizes the lane speed monitoring conclusions. So to conclude, I think the whole idea is, we've always dealt with these things kind of in isolation. We said, let's really focus on safety, and we haven't really looked at the other ones. But now we're starting to see when we develop these new connected and automated vehicle applications, we're now seeing this more holistic way of looking at it and combining these different things together. And then next is the step of actually tuning the parameters so that we can get those overall benefits. And so I think we're going to see more and more of that as we move forward, and we're going to have some pretty big impacts as we move forward with both connectivity and automation. With that, I'll conclude. Thank you.
So